I'm Gur Huberman, a professor of finance at Columbia University, and it's my pleasure and honor to introduce today's speaker, who is Professor Eli Ben-Sasson. Eli is a professor at the Technion in Israel of computer science, a leading cryptographer who a few years ago has been seduced by cryptocurrencies, and now is a founder and leading a firm that applies his cryptographic ideas in an outfit called StarkWare. Is that the name, Eli?
Yep.
So and his major contributions were on zero knowledge proofs, and he'll tell us about the marriage between zero knowledge proofs and cryptocurrencies as he envisions that. So just go for it, Eli.
Okay, thank you very much, Professor Huberman. So just I'll just add and say, first of all, you know, I left Technion, so I'm no longer a faculty member there. I'm focusing solely on StarkWare, where I am a co-founder and president. And I'd like to tell you a little bit. So I looked a bit at the talks that were before, and I enjoyed what I saw. They were generally speaking about economics, and this one is going to be a little bit more about a technology, but this technology, I think, both poses very interesting questions and also raises very interesting possibilities. And please feel free to interrupt and ask questions and discuss as we go along, okay? So I'm going to tell you about ZK Starks and how they can be used to solve blockchain scalability and privacy problems. And feel free to ask questions. Professor Huberman, just you know, let me know when there's going to be something that I need to attend to. So here's like an overview, a pictorial overview of what we're going to discuss. So we're going to talk about blockchains and say a little bit about what are some of their core principles and why they raise certain problems. We're going to mention a particular one, Zcash, which uses some of the technologies I was involved in. We're going to mention beautiful mathematical results that led to things like the Turing Award in 2012, given to Professors Shafi Goldwasser and Silvio Micali, and more recently to Professor Avi Vigdorson. He received the prize, the Abel Prize in Mathematics, I think something like last week or 2 weeks ago. Also my PhD advisor, and he's a scientific advisor to StarkWare. We're going to tell a nice Chinese fable about the empty pot, and we're going to talk about some practical things like our products. So a lot to cover. Let's start with a paradox. Bitcoin is relatively new technology. Ethereum is even newer. They were launched, you know, between 5 and 15 years ago. So why are they so slow compared to older payment systems like those used by banks and credit cards? Why is it that Bitcoin and Ethereum can only process something like 10 transactions per second or 10 TPS, whereas Visa processes, you know, 1,000 to 10,000? And things like Alipay and similar things process hundreds of thousands. I mean, you would expect, I mean, there's no lack of bandwidth on the internet, and we all know that Bitcoin and Ethereum run on the internet. So why are they so slow? The reason has to do with a very beautiful principle and the way that they operate, which is very different from the traditional model we all are familiar with. So the traditional model of the trusted party, banks, for instance, operates under the premise of delegated accountability. How do we know that the banker is not going to steal my money? I mean, especially these days when my money is represented by some bits inside a file, there's nothing that technologically prevents my banker from, you know, just annulling my account and then, you know, transferring all the funds to his account. The reason this doesn't happen every day is because we have this system based on delegating the process of checking the accountability and the integrity of these systems to various people like lawyers and accountants, and we ask for signatures on these things. So This is the way that we have the system operating, and it's been working pretty well for millennia. Blockchains, for better or worse, I think for better, try to disrupt this and have a different way of working, which is inclusive accountability. Roughly, it says anyone with a laptop and internet connection is invited to come and check and verify all the transactions in the system. And it's crucial that we maintain inclusive accountability, so say the blockchain folks. And it's crucial that we do not start excluding people from being able to monitor and hold the system accountable. So hence, it's very important for blockchains that we maintain the principle that anyone with a laptop, even doing other things, can sign in once a day or run this process as they're doing other things, browsing the internet, and their computer will be monitoring everything that happens on the blockchain. And people actually do this. So to give an example, when StarkWare was asked by the Ethereum Foundation to provide some new Stark-based cryptographic primitive that is much better than what existed previously, it was very important for the Ethereum Foundation inside the grant definition to say, it must be something that can be run on a quad-core laptop with 16 gigabytes of RAM, which is something that probably costs today under $1,000 to buy, maybe even less. So it's very important for them to make sure that the technology can run on very simple machines. And this is something that if you go back to the banks and Visa, this is not a requirement for those systems, right? It's perfectly fine for the regional, whatever, bank or the processing unit or Visa processing unit to process, to buy a very large server and process things at a very high rate. This is something that blockchains are not willing to afford by ideology. Okay, but once you have this principle, you can immediately see why both privacy and scalability are significantly compromised. If everyone is invited to see each and every transaction in the network, then goodbye privacy, right? And the fact that you are advised to pick a pseudonymous key once in a while doesn't really mean that you have your privacy. It's very easy to de-anonymize the whole payment network, and there are companies like Chainalysis that are actually doing this very profitably and very successfully. So privacy is pretty much eliminated in the original blockchains as we know them. And scalability also suffers, because if we were to go and 10x the amount of computation, let's say in Bitcoin or in Ethereum, it's not that there are not enough computers in the world to do this. No, it's very easy to do that. But maybe my laptop or the laptop of someone in Sri Lanka wouldn't be able to monitor the system. And this is a principle that blockchains are not willing to accept. Okay, so this is why the principle of inclusive accountability, which clearly should resonate, it resonates with democracy and even direct democracy and with oversight and transparency. This principle leads to very limited privacy and scalability. And cryptographic proofs, that are the main topic of this my talk, solve both problems, and that's what I want to focus on. So first, I'm going to focus on privacy, okay, and on fungibility. And I'm going to do this through the story of Zcash. I was one of the founding scientists of Zcash, and it is based on a particular proof system called the ZK Snark that I and my co-authors have researched, and there's a bunch of other teams that worked on this. So, and later on, we're going to talk about scalability, which is the main thing that StarkWare and ZK Starks deliver today. So maybe before that, I'll pause here. Gul, are there any questions so far?
Not at the moment, no. You can...
Okay.
Go ahead.
Okay. And I encourage folks to raise their hand and ask if there are questions. Okay, so the next part is going to be about Zero Cash and Zcash. So I started researching proof systems in their mathematical incarnation in, sorry, just one second. I just want to close the door here so we'll be a little bit more quiet. Just one second. I started researching cryptographic proofs around 2001 when I was doing my postdoc at Harvard and MIT. And then slowly I started implementing them. This was around 2008. And 5 years later, I was wrapping up a sabbatical in the US, and I went around a bunch of universities and wanted to give public talks on the implementation of cryptographic proofs. And the very first part of slides would say, why do we need such proofs? And my experience was that it was very, very hard to explain to anyone in the conventional world why someone would need a cryptographic proof. Why would, should the bank be the one proving something to its customers? Maybe the customers should be proving something to the bank. It just doesn't make much sense. No one needs it. The system's working perfectly fine. And then I chanced upon the Bitcoin 2013 conference, which was in San Jose, and it was the most electrifying conference I ever attended. Definitely starkly different from the academic conferences I attended before that. And it was electrifying because there was this messianic feeling in the air that we are now changing history and we are changing it for the better. So I'm too young to have been at Woodstock, but maybe it was something like that then. And I gave a talk there, and I remember that after the talk, immediately, people didn't come, as in the academic world, and ask, wait, I just don't get this. Why would you need this? It doesn't make sense. Rather, many of the core developers of Bitcoin at the time, they came up and said, wow, this is, here are like 5 different things that we would do with this if we had the code. We would do with it tomorrow. It's really needed. No need to explain why this is needed. And this, to me, was the watershed moment, or the point where I swallowed the red pill or went down the rabbit hole. So started with my peers working on using this sort of cryptographic proof engines that we were building and doing something within blockchains in them. And there was some academic paper called Zero Coin that used a very rudimentary kind of proof system to show how to get better privacy. And we had this much nicer and better engine called the ZK Snark that we were working on. So we said, hey, why not bring this together? And we wrote this paper and wrote code called Zero Cash that shows how you can solve a problem that I'll explain in a minute. And this led quickly to the foundation of a company called the Zcash company. Now it's called the Electrocoin company. It launched a coin towards the end of 2016. Coin is called Zcash. And now I want to explain what it does and why this is interesting and important. So we're going to talk about privacy and how cryptographic proofs can help solve privacy or make it better. So let's look at a typical Bitcoin transaction. Alice pays Bob 10 Bitcoins, which right now is like $300,000. And what does a transaction look like? So Alice has some key, some public key, which looks like a random number, and Bob has some random number. And the transaction pretty much says, key of Alice, comma, key of Bob, comma, 10 Bitcoin. This is transmitted for everyone to see. And then the miners, they check that Alice's key indeed has 10 Bitcoins and, credits Bob's account and debits Alice's account, something like that. Okay. This is how a Bitcoin transaction looks like. Now, you would think that Alice and Bob have privacy because they use these random keys, but actually the same key is used, or keys associated with it, are used across multiple transactions, and therein lies the problem. For instance, let's suppose that Alice received her salary from Charlie, and Charlie has one more employee by the name of Andy. So Alice, when she receives her transaction, can use a browser to see whether the same ID from which she received funds also send funds to some other address. And typically this will be the case. And maybe it will be every first day of the month that this thing happens. So Alice knows that there's one more employee, that's Andy, and she can check and see whether, what exactly is his compensation. And this is something that, of course, Charlie wouldn't want. Maybe Alice wouldn't want it either, or at least Andy. And likewise, when Alice pays Bob, Charlie can look and see, where Alice is spending her funds, and that's also undesirable. Now, often people think that you need financial privacy only if you're a criminal, but that's of course not the case. You cannot imagine any business that is successful and has some competition willing to have its financials out there and to be exposed, right? Boeing will never use Bitcoin in its current form because then Airbus can learn a lot about Boeing from its transactions. So that's a problem. And as I said, there are companies, very profitable ones, that are exploiting this and offering services to various governments and companies that want to know what's going on in the blockchain and like de-anonymizing stuff. So this limits the appeal of blockchains. Businesses can't allow their competitors to learn their money flow. It also makes coins non-fungible. One coin is not the same as the other, and you can start coloring coins and saying these are bad coins, those are good coins. Now, actually, in many legal systems, a core principle of money is that it should be completely fungible and uncolored, and even if it could be shown that a $1 bill that I have was I don't know, 2 years ago involved in some crime or stolen from someone, I will not be asked in most legal systems to hand over that $1 bill if I of course have no connection to the theft that occurred many months ago. So you really want coins to be fungible, and that's something that you don't quite get with blockchains. So the main idea in Zero Cash and then in Zcash is to take each one of these payments, and it's a string of bits, and put it in the equivalent of a sealed envelope. And this is actually very easy to do. You can use something like a hash or a commitment, or think of it as some form of encryption. It is something that is extremely easy to do, and it's readily available. You can take any information that you want and put it in the analog of a sealed envelope that no one but for you may open. That's easy. So if we do this for all of our transactions, we solve the problem of privacy, right? And we hide the information. But the really hard problem now becomes one of integrity, right? How, under this veil of secrecy, maybe I could put inside an envelope an invalid payment that just pays me, a million coins that I don't really have. So solving the problems of privacy and anonymity are easy. It's the problems of integrity that are really, really hard to solve. And that's something that can be done with this magical thing called zero knowledge proofs. And these are marvelous constructs, mathematical constructs that have been invented something like 35 years ago, and were very, very sci-fi and abstract, and people thought were impractical to use till we showed otherwise. So now I want to talk a little bit more. Maybe I'll pause here and just so I gave a little appetizer about proofs and some of their properties, that they can prove that encrypted information was computed correctly. And now I'm going to focus much more on this, on what it means. But let me pause here and ask, are there any questions?
Okay, look at my panel and it's pretty silent. There's nobody raising his hand. Nobody typed something in the Q&A. Wait, there's Nomi Die. You want to, who is unmuting here? Fahad? Or him?
Sorry, is there a question, Nomi? Does her hand is not currently raised.
Okay.
Oh,
There's a question
okay.
I see in the Q&A. There's something in the Q&A.
She's saying it was a mistake that she raised her hand.
Okay. No problem. Okay, so let's continue. Let's talk a little bit about integrity. So integrity is beautifully defined as doing the right thing, even when no one's watching. And the story of the empty pot is a beautiful example of integrity. So the story, for those who don't know it, it's highly recommended children's bedtime book. The story tells of a childless Chinese emperor who wants to pick his heir. And to do so, he invites all the children of the kingdom and gives each one of them a seed, asks them to plant it in a pot, water it every day, and then come back with the flower that grows there on the first day of spring. And the competition is the child with the most beautiful flower will be the one chosen for the heir. Maybe the gods have picked him or her. So on the first day of spring, everyone comes holding these magnificent flowers inside their pots. There's only one child that comes with the empty pot, hence the title of the story. And the end of it is that he is the one being chosen. And the reason is that the emperor has handed over barren seeds that can lead to no flower. And only this child acted with integrity, which means only he did the right thing when no one was watching him. So integrity is about doing the right thing when no one is watching, and computational integrity is slightly simpler to define. It is that when you are given a computer program and you run it on your own and update the state of some system, you do so in a way that is with integrity, so that if someone else would have executed it in your place, he would have reached the same new state. Okay, so you just are supposed to run the program as someone else would have. And it's easy to fool ourselves that computational integrity is not a big issue, or that it's like something that we don't really have to solve. But I think it's a little bit like the air that we breathe, that we sort of are used to some prevailing systems for dealing with it, and we think that it's not an issue or that we have it all figured out. So there are four main ways to deal with computational integrity and assure that someone else running a computation is reporting the correct outcome, even when that party has an incentive to misreport the outcome. So, sorry, just one second. I just want to.
Eli, while you're moving things,
yes,
I have a question here, which you may want to defer to the end, or you may want to address now. And this by Ayan Bhattacharya. How would zero-knowledge proofs relate to more conventional mechanism design? If all incentives are properly aligned, that is mechanism design, a social planner does not need to explicitly watch over implementation. So you may want to incorporate that either now or at the end, or maybe open it up to discussion.
Yeah, that's a terrific question. So
that's an economist question for you.
Yeah. So the economist is asking, it's a terrific question, is basically, if you want to have a computational integrity and people operating in the right way, just make sure that you have the incentives properly aligned, so that they will be, truth eliciting, or the rational choice will be the one that is used. So I would answer that first of all, often it is very hard to design mechanisms correctly, right? And then really properly incentivize. At other times, it may be too costly in ways that you don't want to allow for or pay for it. because it would violate some other principle that you don't want to do. And lastly, if you have things like proofs at your disposal, you can completely eliminate certain attacks or behaviors from happening. And then you simplify, even if you're going to look at mechanism design, you can simplify your design space because you know that certain things are going to be prevented. It's like a little bit like, if you have a gravity that just constantly is pulling people to the ground, you don't have to worry about people flying off into space. That's one thing you don't, or bumping their heads on ceilings, right? So you still have to make maybe various places safe, but you don't have to worry about sharp objects that are attached to the ceiling harming people that just fly into them, right? So I don't know if that's a good analogy, but so it's definitely a good tool to have at your disposal. Just like I guess economists would agree that having things like laws or things that say if you do such a thing that you're going to be punished is also good for mechanism design in the sense that it constrains and makes your search space or design space a little bit smaller and simpler. Okay, but it's a terrific question. And by the way, I think it's an extremely interesting question of how to take zero knowledge proofs and mechanism design and mingle them together. I remember I talked a little bit with Professor Tim Roughgarden about the AP 1559 and their the new fee allocation mechanisms for Ethereum. And like the very first premise in his analysis of the new mechanism designs is that, well, you cannot really run anything like a second price auction on a blockchain. It's all about first price auctions. You're really, really limited. And the first thing I said to him was, if you have zero knowledge proofs, then you can actually start thinking about things like second price auctions, and you can actually design them. So, and second price auctions are a very useful tool in mechanism design. So, zero knowledge proofs give you those things. Okay, so I want to mention 4 ways that we know of for solving the problem of computational integrity and making sure that people are operating the computations in the way they should. Okay, let me just go over them. The simplest one to explain, the 2 simplest ones are naive replay and delegated accountability. Naive replay is what we do when we receive a receipt, usually handwritten, with a computation of some grocery bill or some restaurant bill. And we run the same computation ourselves again. And this is the same mechanism that the nodes following a blockchain also use, right? Each and every transaction and each computation, they're going to run and check that it is the same as the blockchain is reporting to them. So it works very well, but is extremely inefficient. The second one is delegated accountability, which is the conventional, banking and financial system. We trust some parties, but then we check them, or we send certain parties to check them. 2 more exotic ones. One of them is called the trusted execution environment. It says something like this: suppose Intel or some other chip producer could give you some sort of the analog of some Faraday cage, something, some computational device that you can only send encrypted things into. And there's a machine that is, by assumption, a piece of hardware that will never deviate from doing the computation as it should. And before it sends things, it signs them with a key that only it has and no one can ever reveal. So you get computational integrity. And the last one is cryptographic proofs, which is the stuff that I do, StarkWare does, and a bunch of other colleagues and collaborators do. So let's compare them. Naive replay has a lot of adoption. When we check grocery receipts, we might do this, and we do this in blockchains. It has really no privacy and no scalability because everyone needs to check everything. But it's very trustworthy because you can just check everything yourself, and it's intractable to compromise, right? As long as I run a computer program and check the computations that you are doing, then I cannot be fooled. Delegated accountability has very good privacy and scalability, right? This is the banking system as we know it today. You have to trust humans, and hence it is pretty easy to compromise over time. Now, the trusted execution environments give you very good privacy, and scalability is problematic because of this question mark about intractability of compromise. So Intel would like you to think that it is physically impossible to extract the keys and open up this hardened piece of hardware, but that's not the case. Previously, there were some hardware modules called trusted platform modules, TPMs, that the industry wanted to use to solve digital rights problems. And this just failed catastrophically because it was very easy to extract keys and sort of crack open these enclaves. And we're already seeing the cracks in SGX, which is this new hardware premise. So I don't think a lot of value is going to ride on such trusted execution environments ever. The last one is cryptographic proofs, and those are where Starks and Snarks and Zcash and StarkWare reside. They're not yet, broadly adopted, but I'm optimistic about them. They give you very good privacy and scalability, as we'll see in a minute. You have to trust cryptography and math, which is good. You don't have to trust the humans, and they are also intractable to compromise. So I root for them, and I think they're going to win over. Now I'm going to dive a little bit deeper into what cryptographic proofs of computational integrity actually mean. What are their properties? But let me again pause and ask if there are any questions about
and you may want to defer it until that's up to you. Is it possible to derive a uniform measurement of computational integrity in a given scenario and its corresponding value or price? In contrast, is there a model to derive the cost of different security modules? So I'm not sure you want to address this now, or maybe after you conclude the main points.
My main problem with this is I'm not sure I quite understand the question. Maybe I'd be happy to try and answer it now. I like to answer things interactively, but maybe the person who raised the question is willing to elaborate, speak.
Fahad, can you open this up somehow? Let the
Yes.
first.
I've allowed the speaker to speak, the person asking the question to speak.
Hello, Professor. Professor.
Yeah.
I would like to persuade people to adopt the new crypto methods to ensure their integrity, but they need to know the cost and what they cost and what they gain. So it is necessary to invent a measurement of the value what integrity brings. So, but for me, it is hard to conceive such measurement.
I would say that it's something like a dollar value that can be taken, that resides in a system. Later on, I'll share some of the systems that StarkWare has built, but they all operate similarly, where basically funds are locked inside this one big account, and then the integrity or the divvying up of the total sum among the different accounts is done by method of proving stuff. So if what you have locked up is, let's say, $100, someone who deviates from integrity could steal the $100. And if it's a whole blockchain, then the whole value of the blockchain could be stolen, which probably would mean that its value measured in something like purchasing power or in US dollars or some other external unit of account would go to zero. So I would say that with, and the same thing with the banking system. Suppose, you take a bank and now it loses all of its integrity. So it means that all of the accounts there are compromised and someone could basically steal essentially all of the money that is deposited with this bank. So that is the cost of integrity in these systems. I think it's not hard to say or I'll give it a different example. Suppose I am asked to compute my tax and report it.
Yeah.
So if I do not operate with integrity, I could, the value I could extract from it is the total amount of tax that I, do not pay and should pay. And that is, within a given system, one can compute it.
Eli, there's another question.
Yes.
Why didn't you mention multi-party computation here? Or maybe you should, or maybe it's a different topic.
Multi-party computation, I agree that one should mention it. Multi-party computation, that's a terrific question. So multi-party computation deals even with integrity so I was referring more to the case of a single party doing a single computation, which is the case that, something like SGX can help with a trusted execution environment, or if you have the bank running the computation and someone is holding it accountable by inspecting it, those are the cases. This question is correct in pointing out that sometimes you have computational systems that are composed of many different players, and you want to have the system as a whole operate with integrity. This is a much more complicated problem because you want many, many additional properties, right? You want it to be, the question is how many participants do you assume are honest and how many of them are malicious, and or do they want to, do they want to steal funds, or do they want just to learn things that they shouldn't? But I agree that multi-party computation is also something that in a broader sense can be applied to these questions. Stated differently, zero-knowledge proofs and proof systems are a simplified version of a more general paradigm known as secure multi-party computation. I'll try to address that a little bit later, but that's a good suggestion and a good comment.
Okay, we've exhausted the questions for now, so proceed with the highway.
Okay. Thanks. So terrific questions. And let me continue. Okay. So how should you think about a proof of computational integrity? A good way to think about it is by example. So this receipt from the restaurant is an example of a proof. It proves a statement. The statement being proved is that you should pay $89.50. The party generating the proof and wanting you to believe the integrity of the statement is, in this case, the grocer or the restaurant owner. And you, as the customer, are the verifier, and you're going to check this proof. And the way you're going to check this proof and decide whether you believe the statement or you don't believe it, it's probably going to be by naive replay. You're going to sum up and run the same computation that you expected the prover to do, and thereby you can know whether it's true or false. So again, a proof is a string of characters that you can write down and in order to convince someone that a certain computation was done with integrity. Now, this kind of proof is error-free, and you can just get it and walk with it, and it has a lot of good benefits, and it's been around for millennia. But that's not what I want to tell you about. I want to tell you about some new versions that received all of these amazing math prizes, and rightly so. And these proofs come with things that will look to you as bugs. They're worse. First of all, you need randomness in order to generate and interact with these proofs. The proof may lead you to believe a statement that is actually false. There's a small probability of error. And you need to do this interactively, as in a court of law, where a party makes a statement, you ask something, they make another statement, and at the very end, you decide whether to believe the statement or not. So it's much more complicated than the proofs that we just have seen on the right of this slide. But there are many things that are amazingly better about these proofs. The first one is this aspect of privacy or zero knowledge, which a good way to imagine it is think that you have a proof that convinces you that you should pay $89.50, but everything but for this total sum is completely blanked out. So you don't know what the items are, you don't know how much each item costs, and still you know that the computation that says you should pay $89.50 was done with integrity. And this is kind of mind-boggling. Like, how could this be? How could I believe a statement? How could someone convince me that a statement is correct without revealing any information about the way this computation was done? And it is mind-boggling, and it is counterintuitive, and that's why all of those amazing prizes went for the inventors and early researchers that showed that such a thing could actually happen. A second amazing property is that of scalability, which says that the time needed to verify the computation is exponentially smaller than the time that would take you to naively run the computation. So let me give an example. When someone will generate a proof for the correctness of all of Bitcoin's blockchain, it's been running for 13 years, the size of this proof, even though the blockchain is hundreds of gigabytes long, and it takes days for a modern computer to verify, the size of the proof of the integrity of all of Bitcoin's blockchain is going to be, less than 10 megabytes. And verifying it is going to take less than a second on a smartphone. And the reason is that verifying a proof is exponentially smaller than the running time that the computation takes. And have no doubt, someone will generate a proof for the full integrity of all of Bitcoin's blockchain. And you can verify it, you will be able to verify it in very small time. I actually hope that the very first party to do such a thing will be StarkWare. But we've done already similar things for smaller statements, but this is how scalability works with these proofs. And in addition, the time needed to generate the proof, so verifying it is going to be exponentially small, and the time needed to generate the proof is not much harder than just running the computation, right? And by the way I got involved in research about proof systems was by improving the running time of provers, because that is the biggest bottleneck of these proof systems. The time needed to generate a proof is actually quite large. And at first I studied it theoretically and showed how to get the proving time down a little bit. And then we started implementing these things in practice. So the second amazing aspect on top of privacy or zero knowledge is scalability, which allows you to compress computations and generate a very succinct proof for the correctness of a computer program, correctness of the execution of a computer program. Another amazing aspect is universality, which means that you can get proofs and verify proofs, not just for summing up items from a restaurant bill. You can get them for any computation that can be specified by a computer program. And you can get them in a sort of uniform way. You don't need to build a different system for each one of these computations. And we'll touch about this in a minute, because one of the things StarkWare is doing is exposing tools that will allow everyone to write programs and then have them being Stark verified in exponentially smaller time, and then deploying this on blockchains. Another aspect of ZK Starks, that's actually the T in the acronym STARK, is transparency, which means that setting up these systems involves no trusted setup. Even if you want the government or the NSA or some, Darth Vader to prove to you something, you don't need to be involved in any ceremony that generate keys or, needs to assume anything about the process by which the proof was generated. All you need is some source of entropy, and then you're good to go. So as long as there's some randomness in the universe that is not controlled by the other party that is proving stuff to you, you can be pretty assured that the statements being stated are actually correct. And the last one that pertains to some kind of ZK Starks, in particular the ones that we're building at StarkWare and the ones I've been researching for 20 years, is that the cryptographic assumptions and the building blocks you need in order to generate them are very lean and battle-hardened. All you need is what's called a secure hash function. In particular, you probably read that there's a lot of discussion of quantum computers being efficient enough to be used in practice, and they will break a lot of the existing cryptography. That's true. That's indeed correct. It would be very good news for me and for StarkWare, because our cryptography actually is not compromised by quantum computers. It is post-quantum resistant. So everything you're hearing here, you're not wasting your time. Even if tomorrow there's a quantum computer, you could still go on using it. So let's take this and now apply it to blockchains, and we're going to take the scalability part. So the privacy I discussed a little bit with the example of Zcash. Let's talk about scalability. What we're going to do is take a bunch of transactions, those are the red squares on the left, and send them to a prover, which is some big machine. The prover churns and turns around and does some things and generates a very small, succinct proof that is then sent to the verifier. The verifier, simply by checking the proof, knows that the statement that the prover is making must be correct. So what we're going to do, let's look at blockchains as they work today. Each one of the nodes that is participating in the blockchain, again, this could be my or your laptop, is constantly getting transactions and reports of new blocks and checking each and every transaction there and checking that everything's fine. So, and then updates the state of the system and all the accounts. And we have this replicated machine over many, many places. What we're going to do with our technology is replace it. And we're going to ask the nodes to run a computer program that just verifies proofs and records a very short fingerprint of the state. And then what the nodes are going to do in the new system is going to be just to verify proofs and then accept a new state and repeat this again. And this is something that is not only theoretically possible, that is something that we have already been doing for quite some time in production with real systems for more than a year by now. So I just want to mention that there's, and I know this is not a talk for cryptographers and mathematicians, I just want to say that there's a huge Cambrian explosion of ZKPs. They come with many, many funky names, and they fall under different families and so on. I have a blog post about it and a video where I go over these different aspects and then try to explain my understanding of them. I just want to say that the TLDR, which is if you really want the proofs to be very, very short, as was the case with Zcash transactions, you're going to use something called a Groth16 snark. And for all the other use cases, you really want to use a Stark. They are post-quantum secure, have the fastest proving time, they're the most scalable, and probably the most future-proof by the Lindy effect, because they've been around, or the building blocks they use have been around for longest. Okay, and you can read more. I'll share with Professor Huberman my slides, and you can then click the links and then go see more and learn more. Okay, so we talked a little bit about the potential use cases of Starks and scalability and also zero knowledge for hiding things. But now I want to tell you a little bit about the way we actually apply these things today. We've already deployed them on a number of systems. If you recall, I said that blockchains, Ethereum and Bitcoin, they reach rates of something like 10 to 20 transactions per second. So our very first system that was launched roughly a year ago reaches a TPS rate of 9,000 for trading and twice that for payments, which is pretty much on par with what the Visa payment system uses. We've also significantly reduced the cost of doing operations, for instance, minting a non-fungible token. If you do it on Ethereum, it's going to cost you roughly $40 because you need all the nodes of Ethereum to verify all of the computation that has to go into generating a non-fungible token. With our technology, we did this for our customers, and we minted hundreds of thousands of NFTs inside a single block at a cost of 1/5 of a cent per NFT. That's a factor of 20,000 reduction in the cost of doing this thing using this technology, which this uses the scalability of the proofs, the fact that verifying a proof is exponentially smaller than running the computation naively. And we also launched a system for margin trading called DYDX. It's already done more than over the past 2 months that it's been operational. It already settled more than $2 billion of volume, and it's humming and chugging along quite nicely. All of these systems are written with a programming language that's called Cairo that allows programmers and developers just to write whatever functionality they need. And this code is executed, and then proofs are generated for it automatically. And these proofs are then sent automatically to blockchains. So we have this full system that allows you to basically write arbitrary logic and then get proofs for it. And Cairo is a very simple programming language. I don't know how many of you actually program. It is said that code is law and code is also mechanism design. So I'm guessing some of you have programmed, or you have students who program. So I urge you to go and or send your students to learn Cairo and start writing programs in it, because the integrity of these programs can be automatically verified. We have a very extensive tool chain for doing these things and a bunch of examples. And actually, we're now opening a full layer 2, or something that is like a blockchain, but relies on Ethereum's security for it, but will have much larger scale. And this system is going to be called StarkNet, and it will operate or utilize this scalability aspect of Stark proofs, so that you can run computations that are much more intensive and get a proof for them on the blockchain, and use the blockchain only to check proofs and run big computations off-chain. So it's going to be deployed roughly next week, the very first phase of it. And you can write smart contracts. Here's an example of such a smart contract. Again, this is an automatic market maker that will be running at much lower gas cost, and anyone can write and deploy their own contracts on this thing. So again, I urge you, if you're interested, to go ahead and learn this stuff. So here are the places where you can, QR code. I'll share my slides with Professor Huberman, but definitely you can also go and start join the discussions and learn. And I am also going to share a lot of further resources on both math and education about it, and what you can do with proof systems in general, and with ZK Starks and its programming language in particular. This brings me to the end of the presentation that I prepared. I can now answer questions or open it up for the discussion about the positive and advantages and disadvantages of running proof systems over blockchains and outside of blockchains. I'll just give 2 examples before I hand it over to discussion, and I'm very happy if, I'd like people to converse and raise questions. I just want to say that, first of all, I think that computational integrity is going to be extremely important, not just within blockchains, because you would like to have governments, monopolies, large institutions prove and assert their integrity to the citizens in society. And something like a ZK Stark is, the cryptography behind it is something that even the most powerful of parties cannot cheat on. So, for instance, in the academic white paper that described the implementation of the first ZK Stark, the example we gave is that of a police department wanting to prove that it checked whether a DNA profile of some very powerful person who's running for president does or does not appear in the database of forensic DNA taken from crime scenes. And we showed how this, we actually wrote programs for it and showed how this can be achieved, even if you're not willing to trust the police department, and while preserving the privacy of the candidate, of all other people who are whose DNA is inside these databases. So that's one example. Another example, I wrote a piece about how zero-knowledge proofs can be used for better proofs of solvency. So you want to have financial institutions proving, especially if they have cryptographic assets at hand, you want them to prove that they have either full reserve or whatever fractional reserve that they're supposed to hold. And you want them to prove it in a way you want them to prove it periodically to each and every of their customers in a way that doesn't reveal any information about the total balance of the exchange, and while taking into account each and every customer's assets. These are things that are impossible or that are not done today by financial institutions, to the best of my knowledge, but you would really like them to be a standard, and I believe they will become a standard as this technology percolates from the world of blockchains and enters the world of standard systems in society at large. So there are a lot of applications to proof systems, cryptographic systems, both in terms of scalability and privacy. And with this, I'll end my talk, and I'd like to, I hope there'll be some discussion or some questions.
Okay, Eli. So let me actually start with two questions which are related, and they're asking you to play your own game, namely, provide some information on how zero-knowledge proofs work. And then the follow-up question is how Stark proves some simple messages. So if you can somehow capture the essence to economists who are not trained in computer science, let alone in zero-knowledge proofs. So how they work in principle and how Stark works. And then we'll move on to other questions. You can do justice to these two questions.
It's a terrific question. And I think I have a good, there's a way I have of trying to explain it. Okay, we want to discern very quickly and efficiently between truisms and falsities. And let's start with the physical world, okay? Let's suppose, and I'm taking a very, simplified example here, but let's suppose someone is accused of committing a crime, let's say theft. And when prosecuted, the defense says, on the day that the theft has occurred, I was not in the country. And now what will happen is there'll be this interactive process of, asking the defendant certain questions, right? Okay, if you weren't in the country, where were you? Can you please provide an airfare ticket? What was the weather on that day, in the city that you claimed that you were? Do you remember anything outside the hotel you resided at? And by this process, often, very quickly, you will discern between truisms and falsities because, truth shines, or it has, physical reality has this sort of, there are many, many interconnecting facts and things that are consistent with reality. And if you want to construct a lie, then it will be inconsistent very easily. You may not know what the weather was because you actually weren't there, and then you'll be saying something that will be very easy to contradict, or things like that. So, okay, taking a step away, what has happened here? Because physical reality has all of these interconnections, right? People, in many cases, are very good at quickly discerning truisms from falsities. So we would like to take this principle and apply it to computation. So I'm saying that I ran a computation, for 1 billion steps and reached a certain result. And you would like to devise a way for it to be very easy to ask me a bunch of small questions about the nature of the computation that I did and see whether I'm speaking the truth or not, okay? So you want all of this redundancy added to the steps that I took, the analog of all of these external factors that I should experience as I'm walking around in the physical world, let's say traveling outside of the country. Now, the way we do this in a computation is we ask the prover who is making the statement to create, this redundancy and have all of this extra information arise. And the way this extra information is arised is by adding redundancy in the form of what's known as an error correcting code. So instead of just stating or recording the steps of the computation. Let's suppose that there were 1 million steps in the computation. I was updating the state of some system by doing 1 million small steps. Now what I'm going to do as the prover is, first of all, I'm going to do those 1 million steps and then add another 100 million steps to just add a lot of redundancy via what's called an error correcting code. And now I have this much more elaborate statement with a lot of interconnections between different parts of this bigger statement. And what I'm going to do with it is I'm going to submit it to some court. I'm going to put it inside an envelope, commit to it in a way that I cannot change it, and say, here is my deposition, right? This is not just the computation that I did. This is a lot of redundancy added on top of the computation. And then what happens is, because of this redundancy, when I am asked to answer a few samplery questions about connections between the various parts of my computation, it will magically be the case that if my computation was correct and my statement was correct and my end result was correct, I will always be able to answer, in a satisfactory way, all questions I am asked about. The analog of what was the weather, what is the sum of these two parts, what was written in this cell at this time, what was written in that cell times whatever, what was written 5 cells later, and all kinds of questions like that. I will be able to open up and show that my answers to all of these questions were correct. Whereas if I'm trying to cheat and I'm trying to prove a statement that is actually false, then there will be a lot of local inconsistencies. The analog of saying, oh, the weather was hot, but actually, 2 questions later, I will be saying that I wore, a coat on that day. It was raining, and things like that. So this, again, just summarizing, the way proof systems work, and ZK Starks in particular, is you ask the prover to take a computation, let's say running for 1 million steps, add a lot of redundancy to that computation by using an error correcting code, committing to this more elaborate data, and then answering a very small set of local random questions. And the math shows that if the statement was true, all of these questions will be answered in a satisfactory way. Whereas if this was a lie, with 99% probability, some inconsistency will be exposed.
This is beautiful explanation. I have heard various explanations in knowledge proof, but this one is really excellent. So let's move away from that to applications. At least one brief question. Can you see application in traditional banking?
Yes. Well, okay. Yes and no. So traditional banking, I think, and a lot of, in insurance companies and many of the financial institutions, right? You come and you enter the building, and there's this beautiful big marble, whatever, entrance, and it signals to you, you should trust us, right? And people are wearing very fancy suits and nice Rolex watches, and like this is signaling to you that, look, put your trust in us. So these systems are based on trust. To quote, Paul Krugman, he explains it this way: there's this amazing technology that humans have honed over millennia, which is called repeated games and reputation. And basically, the banks are there not just for one run. They want you to return. They're going to profit much more from you knowing that the bank is trustworthy. And that is the incentive for them to operate with integrity. Now, for this model of banks, I think that the whole notion of a proof doesn't make sense. And let me explain why. You have the bank and the customer. So the bank tells the customer, if you don't trust, first of all, why on earth would you not trust us? But if you do not trust us, why, please don't, just don't deposit your funds with us, period. Go find some other place, okay? And the bank tells the customer, because you trust us, you, the customer, will basically send all of your information to us, and you will not do any computation. All computation you want done, we will do. And if you think about, we all have bank accounts and we all probably have these mobile apps, right? The mobile apps, right? They're very pretty, GUIs, right? Graphical interfaces. But what happens? They authenticate us, right? So the bank is just making sure that the inputs being received from this graphical interface are really from the customer. But then these are instructions that are only fed into a computer that is run by the bank, right? The bank doesn't tell you, okay, just walk around with a bunch of money, tell us at the end of the month what happened to it and how much is left. No, the bank keeps tabs on everything we do. And we can just authenticate ourselves to it and then give it instructions, ask it to run the computation. So the bank does not need its customers to run the computation, it doesn't trust them with it. And the customers are putting all of their trust in the computational integrity of the bank, okay? However, there are two scenarios. One is that the banks, for various reasons, may, sets of banks may not trust each other and may not be even interested in finding a third party that they will sort of collaboratively trust. And the second thing is that a bank, with respect to its employees, may want to know that they are operating with integrity. And those are two use cases, right? One, when you have a bunch of trusted parties that do not trust each other, like 5 banks that want to do something. And when you have a large entity like a bank that wants to have better assurances of integrity from its employees in various subparts of it. So those are examples where maybe someday conventional banking systems might want to use blockchain, but it's not the case yet, sadly for us.
Okay. So let me find another question here. Somebody, Daniel Ogot asked, does the Mina blockchain, I'm not sure what it is. Do you know what Mina is? The size of a few tweets fit in your framework. So maybe you want to say what is Mina blockchain? I don't know.
Yeah. So Mina is a blockchain. I think they went live very recently. It is a blockchain that promises that all of the history of the blockchain can fit inside, less than a kilobyte. And what they actually mean, and this, they achieve it, or this is claimed to be achievable by proofs, right? So what you will have is that whenever there is an update to the state of the system, there will be a very succinct proof that this state was updated correctly. And then all that you will receive is the new state, a fingerprint of the new state, along with the proof that it is correct. So it operates under very, very, well, okay, from a high level view, it is exactly a special case of or an application of the use of cryptographic proofs for scalability, right? Going back to this sort of bigger landscape of particular mathematical proof systems and the way they operate, Mina uses a different flavor than ZK Starks. In particular, it is not post-quantum secure. It has some other properties. It uses a recursive SNARK for those familiar with it. Yeah, it's for the purposes of this talk, it is another example of the use of proof systems to make very short proofs of computational integrity for pretty big statements like blockchains. Yes.
Okay, so we don't have to finish it at 15. I mean, my time it's 12:15. I mean, wherever you are. So if you're willing to stay a little longer, there's more questions here.
Yeah, no problem.
The next question is, do you see ZK Stark being useful in permissioned distributed ledger technology?
Sorry, again?
You see your ZK Starks being useful in permissioned distributed ledger technology as opposed to permissionless. You see the relevance of this technique?
Yes, I guess it's the same. Yes, so permissioned could use it. I just think that often when you're in the permissioned blockchain, you see there's already a change of the trust assumptions. So permissioned means that there's a small whitelist of players that are allowed to update the system. Now, so it's a little bit like this case where I said that maybe there are, like, 5 banks that want to collaborate and they don't trust each other that much. So a permission blockchain is a little bit like that, right? In saying that there are only 5 nodes that you really trust, but maybe you want them to prove stuff. So practically speaking, I'm not aware of permissioned blockchains today that use zero-knowledge proofs for scalability, and I'm not aware of permissioned blockchains that use the Zcash-style privacy, even though that could be another area. You could say that the permissioned operator, for various reasons, is not interested in knowing what is going on in the payments, right? I'm not aware, but it could be an application one day. Yes.
Okay, another question is, can zero-knowledge proof account for correct but incomplete set of records? So there'll be consistency, but not completeness, I guess.
Yeah, this really depends. That's a terrific question, because, okay, it really depends on what is specified by the computation. So for instance, if the computation is, take a payment system, right? So, there are a bunch of user accounts, and anyone can, by signing a payment, can transfer funds. And suppose that there were 100 transactions requested submitted to this mempool or to the blockchain or to the operator. And for some reason, the operator decides that he wants to censor one or some of these transactions. Then definitely it's possible for the operator to generate a proof that will have only 99 transactions processed and never include this, the 100th transaction. Yes, this is possible. But in other cases, suppose you define a computation ending in success only if a number of different things happen, like you need to update 5 different files. Until you updated all 5 files, transaction is not completed. In that case, you won't be able to generate a proof that is convincing and for a computation that updated only 4 of the files. So it's really all about what is the computation that you want to prove correctness of, and whether it is legitimate for it to do a partial update or not.
Okay, then another question is, can you give a non-interactive example of some messages on the blockchain?
Sorry, again?
So let's see, I'm reading this and I'm not sure what. Would you mind also giving a non-interactive example for some messages on blockchain, say the validity of a transaction? So I'm not sure there's room.
Yeah, I'm not sure I'm answering the right question, but I'm saying, okay, the way that StarkWare systems work is that they receive, 1,000 or 100,000 payment transactions, requests for payments, and then you generate one Stark proof that updates the state of the system based on all of these 100,000 payments. Each one of them is, a single non-interactive statement. I'm not sure if this answers the question. Maybe the speaker wants to wants to explain what the question is.
Yeah. Meanwhile, we have one more question. Oh yeah, go ahead.
Okay.
Yes,
thanks.
yes.
So I'm curious about, like, for example, the example you give, right? For example, there's a transaction, and I'm just curious about how Stark actually works, right? Rather than just metaphors, but actually how does that work, maybe in a simple way, so that, and I assume it's a non-interactive ZK proof. So I'm just curious about how such proof actually work. So maybe in a not too high level, but also not too low level fashion. I don't know whether the question.
Yeah. So first of all, I just want to say that in the resources that I send, there's actually there's a sequence of 5 blog posts that explains how, for a very simple computation, basically the Fibonacci sequence, which is this iterative summation, how you get a proof for its correctness. And I have a bunch of mathematical talks that you know what, I'll add before I send the slides to Professor Huberman. I'm also going to add just a link to specific talks that look very specifically at how do you get a proof for some statements, and they go by, you know, you need to say a little bit about polynomials and Reed-Solomon codes and things like that. So I would just say that here at this high level is that you know, the computation is a set of steps, right? There's a state of a machine. Maybe it's given like by, you know, sequence of whatever, 100 bits. And then you're sort of modifying it time and again, right? That's how a computer works, right? It's, you know, I don't know, adds 2 bits, writes them to some other part, reads from some other part, multiplies, does a bunch of things. Okay, so you sort of start by recording this thing called an execution trace for all of the computation, right? And then you take this execution trace and you add redundancy to it. So the way you add redundancy to it is just like the way that you do, you know, interpolation. So any 2 points, there's a line that passes through them. Any 3 points, there's a parabola, right, a degree 2 polynomial that passes through them. So what you do is you take these million points, and there happens to be a degree million polynomial that passes through these points and interpolate them. And then you take that polynomial, you interpolate it, and you evaluate it on, I don't know, 10 million points or 100 million points. And you receive redundancy in this way. So you took the information about the computation and you added a lot of redundancy to it by this particular method. And then you have this much larger table and you cryptographically commit to it. You sort of put it inside an envelope and say, you know, this is the information. And then you're given, either you're given interactively some queries about it, you need to open some parts of it, or if it's non-interactive, you're going to take that commitment and sort of feed it into a cryptographic function that will give you randomness, and you're going to answer the random queries. And you sort of expose different parts of this encoding, and they should all somehow fit together in a way that it's going to be hard for me to explain to a bunch of economists in like 5 minutes. I mean, that's why, you know, Professor Vigdersen got the Abel Prize, and Professors Goldwasser and Mikali got Turing Awards and a bunch of other things. It's a bit, it uses polynomials over finite fields, probability, complexity theory, linear algebra, and a lot of beautiful I mean, probability theory and things like that. Yeah.
Thanks. That's actually very helpful.
Okay, so let's conclude. I have a couple of things to say. First of all, thank you very much to Eli. That was a terrific talk. We learned a huge amount. And then Fahad asked me to announce that in 2 weeks' time, we'll have another session by Agostino Caponi, and that will be on NFTs. So you're all welcome to join us. Okay,
perfect.
thank
So
you
thank
very
you
much.
very much.
And we'll go ahead.
Oh no, just I wanted to say thank you to the CBER, and I think the questions were really terrific. And thank you, Professor Huberman, for inviting me to this. And I will send slides, and please, you know, forward them to the participants. And there are some links there.
I will do that, definitely. That's